Yes. Okay. Well, thank you. Thank you very much for the invitation. And what I'm going to do today is I'm going to talk about some very new work. In fact, the slides didn't exist until yesterday, some of them, that I've done together with Erkki Sommersalo, with whom I've been working on Bayesian scientific computing for 20 years. And then to a former student, Nathan Banurek, now doing his PhD at the University of Chicago, and Alberto Bocchinfuso, who just defended his PhD thesis. So the motivation, okay, yes. So the motivation for this work has been pretty much the interest in looking at dictionaries and trying to see how much we can learn if we have a dictionary of potential outcome. But the part I'm particularly interested in is the computational aspect. So I want to look at how we can reduce the complexity of the problem, is if possible, discover and exploit inner structure in the problem itself, and at the same time express desires about or characteristics that we believe are true of both the datum and the way in which we want to represent it. So let me set up this dictionary problem that I'm going to be talking about. And I'm going to be talking about a couple of different aspects of dictionary, say operations with dictionaries here. Particular dictionary matching and dictionary, in some ways also dictionary learning, but learning what there is in the dictionary rather than learning the dictionary as we move along, and in particular dictionary reduction or complexion. So the problem of expressing a vector, a signal, whatever we have, an object that we can encode it in the form of a vector B in terms of a collection of items, of a linear combination of a collection of items, can be expressed as pretty much a linear system. I can write that I want to express B as a linear combination of the columns of D. So I'm writing the system dx equals B here. And the columns of D are the objects that form our dictionary. They are often called atoms because of their somehow unitary and indistinguishable nature. And then there is there is an interpretation also of the vector x that we do not know right now. And I like to think of x as being a weight. So the components of x are essentially the weights that are given to the atoms of B in the representation of the new point. And right now I'm writing down the problem as if B were a linear combination of the atoms, but that is not clear. Many times we have the past collected in D, and we have a new signal coming, and we assume that, or we want to represent it in terms of the atoms, although there may be some discrepancy, in between the representability and what we can actually do. I'll discuss this as I move along. So one of the problems that I've been looking at for the last at least 15 years has been how to write efficient algorithms to compute sparse solutions. So this can apply also to these to dictionary problems. And so let me set up a little bit the stage and then address the issues that come with requiring that the solution is sparse. So let's say that, let's start with the assumption that the datum that we want to interpret in terms of the dictionary has a sparse representation. Meaning that by sparse here, I really do not mean exactly sparse. I always mean sparse in the, say, in IEEE sense. So the coefficients of the contributors contributing atoms that are significantly different from zero are very few. And I call this is the support of X. And the other ones may be numerical noise, so of the order of 10, excuse me, of 10 to the minus 6, or maybe small due to accumulation, or we will see maybe larger than zero, but they will be considered insignificant in the context here. So let's say that we are assuming here that it is possible to represent B with just a few of the atoms in D. So our task is that we want to actually minimize the norm of the discrepancy of the difference between the X and B, restricting this to solutions whose support is small. And we can express how small we want it if we recast this problem in the Bayesian framework in a very efficient manner here. Now, some of the dictionaries that I've been working with recently have been very large in both ways, in the sense that I work with dictionaries whose entries have a very many. So the atoms are high dimensional, and the dictionary itself is overcomplete and contains a lot of atoms. In either case, it has been necessary to reduce the complexity, and the way, the natural way to do this is to replace the dictionary with a low rank factorization. Since this is a matrix, I'm going to write D as the product of two rank K, let's assume that they're full rank matrices, W and H. And of course, if I express in particular, if I don't go through the full rank of D, there is going to be some error. So the representation of D is going to be D is equal to WH plus E, and E is the error in the low rank representation here. So if we discard E in our process of doing dictionary matching, then we can recast the problem and saying that we're looking for H, for a vector H, such that the new datum D can be represented as a linear combination of the columns of W scaled by the entries of H, plus some error that we're going to ignore here. Now, in order to give a physical meaning to the, to the coefficients of H, I'm going to actually also require that H is non-negative. So all of the entries of H are going to be greater than or equal to 0. And in some cases, I can also require that the entries of W are greater than or equal to 0 or have other properties. Now the vector, the term epsilon prime here is one that collects all of the contributions to this discrepancy between the proposal of, the matching of B with the entries of W and B itself. So it could be from the different difficulty in representation of B, but also for some mismatch between the original dictionary D and this, let's say, low rank representation that we're using right now. So at this point, let me outline, because this is going to be, there is it's a multi-phase process here, what we're proposing and we've been using. So what we've been thinking is that to reduce complexity, promote sparsity, and also take into account this error and this error epsilon prime here, which we call, modeling error or dictionary representation error. Now we go through a four-step approach. So the first approach is that we do clustering ahead of time. And in some cases, the dictionary entries are naturally, say, clustering in groups because of the way they've been collected. In other cases, we have dictionaries which do not have a priori any reason of being partitioned into group. However, if one runs blindly and a clustering algorithm, it turns out that there is some, let's say, there are some characteristics of groups of the atoms that make the clustering very natural. So we do a pre-processing of clustering the dictionary, and we subdivide it into subdictionaries. I will call them DJ here. The number can be either of subdictionaries can be decided ahead of time, or it can be determined in a dynamic way. There are many clustering algorithms. Now, once we have subdivided the original dictionary into subdictionaries, what we do is we look at each individual subdictionary, and what I was saying before, that is to say, this substitution or this compression of the dictionary into the product of two low-rank matrices is applied to every subdictionary here. So we get K representations of the K subdictionary DJ into WJ HK. And again, we're going to retain here the property that the entries of H are going to be always greater than or equal to 0. Now, once we have done this partitioning and reduction of the dictionary into a bunch of essentially low-rank subdictionaries, then if we want to keep the focus on our dictionary matching task, what we need to do, or what is a good idea to do, is identifying at this level here which clusters or which subdictionaries are needed to explain D. Particularly if the dictionary is large, but also since we are assuming that B can have a sparse coding, so it can be represented in terms of a few atoms of the dictionary D. In general, there will be not all of the subdictionaries will be active in the representation of B. So in this phase, so in phase 3, the task is going to be identify the indices of the subdictionaries that enter. It's like doing pool testing. If a dictionary is considered to be irrelevant, well, it shouldn't be really playing much of a role in the more, let's say, more costly task. And that takes us to the fourth stage here, which is a deflate and solve type of approach. So we're going to take the dictionary and original dictionary. So we're going back to the representation in the 4-rank representation of the subdictionaries. And we deflate the original dictionary out of all of the subdictionaries that in the previous phase were deemed as not relevant here. So now we can solve the dictionary smaller, in many cases much smaller, dictionary matching problem with the deflated dictionary here. So every task, of course, it has its own computational and modeling challenges here. So let's address let's start with the first one. Let's go linearly from first to last. So the clustering. Well, for the clustering, really, I'm not going to say much. I mean, if the clustering is say already, if the dictionary is already pre-clustered, I like to think of a library. and the volumes had already been formed, we can use the annotation in the dictionary, the original dictionary, or we can apply any or a favorite unsupervised clustering. In our numerical examples and in our daily life, we often use k-madoids because of, to avoid or to lower the effect of outliers here. And so I'm also always thinking that once we're done the clustering, we rearrange the dictionary so that the matrix T is partitioned in blocks of columns that correspond to the subdictionaries. Phase 2, we take each subdictionary, and this can be done nicely and conveniently, independently and simultaneously. We compute low-rank approximations of every subdictionary. And now, in this case, the rank kj here of the matrices, which is also the number of columns of W, which would be relevant for later, is not necessarily the same. So in some ways, it will depend on the computational resources that we have. So we may have a maximum number that we can allow, in particular if every atom is high dimensional, but it will also depend on the true rank of the subdictionary. So when we do this, we keep in mind that some dictionaries may require more W vectors, more feature vectors. We call the columns of W feature vectors because they summarize the features of the matrix that is being approximated here. And others are simpler collection of atoms, and they can be described efficiently with fewer vectors. So when we do this, we compute this approximation. Now I want to keep the entries of every matrix Hj here greater than or equal to 0, again, because I want to interpret the entries as weights. And also, if, as is the case in some applications, the entries of dj or the entries of the original dictionary had some important characteristics. So in some cases is non-negativity, in other cases is sparsity. So we can this is the stage when we can actually express what we a priori believe should be the characteristics of the solutions here, and use a numerical method that allows to fold it into the computed solution. So let's stay with the reduction here. This reduction is very popular in data science and in non-negative, generally in non-negative matrix factorization. So the way in which we've been approaching it is by following pretty much the same procedure as in the non-negative matrix approximations, but when non-negativity of W, so non-negative matrix factorization, both W and H are non-negative. In our case, H is always non-negative, but W sometimes is positive and negative, sometimes is complex. So we relax the requirement for non-negativity for W if it's not pertinent. So we can actually split this, this is the way it's usually done, in alternating operations here, sweeps of alternating operations. So if we start with an original W, sometimes it's just sampling some K columns or K atoms from the original dictionary. Then we compute, we update the columns of H by requiring or by selecting HL to be the vector that minimizes the two norm of the discrepancy between DL and WH. So D is the else column, is the column of the original dictionary. Once we have updated all of W, then what we do is, all of H. Now we have a new H, we replace H with the new values, and we update W by solving pretty much the same problem, except that right now I don't want to write too many transposes. Let's say that we're going to take a W that minimizes, hopefully retaining some of the characteristics of W, the Frobenius norm of the difference between D and let's say the candidate for W, which I call V times H. So the way in which this is done, when I teach data science, mathematics of data science, usually we do this process using a multiplicative, what is called a multiplicative update, which is very fast, but it assumes that the entries of H and W are non-negative in both cases, and also it's not necessarily very open to let's say folding in other properties or trying to push the solutions towards other characterizations, which may be the case in our applications here. So alternatively, what we can do is we can actually think about what I did before. So think about this problem as solving a sequence of, let's say, least squares problem. And we're going to do this by essentially doing sweeps of non-negative or partially non-negative least squares. So this is the update of H. And so we update it column-wise, one column at a time. And once we're done, we are actually scaling the entries of H. And then once we have H updated, we compute W. Again, these are linear least squares problem. And now let's say that we have concluded phase 2. And so we have replaced or we have produced feature vectors and weight matrices for every subdictionary here. So what we can do is we can think that with this, after this operation, the dictionary, the original dictionary, here partitioned into its subdictionaries, is approximated by let's say the dictionary of feature vectors. So we're extracting from the subdictionaries the summary of their content here and multiply by this block diagonal matrix with the H. And this is how we recombine. So now W1, H1, and so on. These are the low-rank approximations of the subdictionaries. And of course, this is not an operation that is exact, so it's lossy, and therefore there is an error here that in the matching. So we can say that the origin, we can call the original dictionary D, our model, the full model, the exact model, and we can call this, let's say, low-rank approximation of D, a reduced or compressed model. We can also go up to the previous line here, and we can think of the W's, we can think of the dictionary of the feature vectors as being a compressed version of the dictionary. So now we go back to the, we keep the focus on our task, which is to match B with the entries of the dictionary. So at this phase, if we're replacing the dictionary with this approximate dictionary, the task is to try to represent B as a linear, effectively as a linear combination of, we can do the combination of H and Z here, a linear combination of the feature vectors. So we're going to have much fewer vectors here, much fewer atoms in the complex dictionary to express B. And what we do is with also this aggregate or partition the vector H times Z. Effectively this is a vector H that we're going to look for all at once here, into the block of entries that correspond to each block of columns of W coming from the different subdictionaries here. And again, this plus epsilon indicates that we don't expect this to be done exactly. So now what is pretty clear that with this compression of the dictionary, we're introducing an error E, and I'm going to refer to this as the dictionary compression error in the rest of this. And we want to study this a little bit. And the way in which we're approaching this error, and I'm going to approach it in a Bayesian framework, meaning that I think that this error is, since I don't know it, is going to be a random variable, and I would like to describe it in the language of random variables, so in terms of probability density function, at least an approximate one. So we write, let's think of the columns, the original columns of D, of the dictionary, as being D times a unitary vector with one in the else position here. And now this would be the exact representation of the else column of D. And I'm writing it now in terms of, I'm introducing the best approximate representation of DL in terms of the complex dictionary. So I'm writing DL as WHL plus DE. There should have been a minus here. I apologize. So this should be a zero sum. So I'm adding WHL and I'm subtracting it off. So the difference between the exact representation and this, let's say, compressed representation is what I call this dictionary compression error. So thinking about this very simple, let's say, trick and a very simple way of introducing this dictionary compression error, we can come up with a scheme, with a procedure to estimate the probability density. So we think of the dictionary itself and the atoms of the dictionary as being realizations from an unknown underlying distribution that we do not know. And we can think of the probability density of this dictionary compression error as being the push forward of this probability here by the mapping that takes D here into this error, which is now computable because, you know, we have the original D, and all we have to do is solve the compressed dictionary representation here. So the way in which we compute HL is just by solving a least squares problem. Again, shouldn't be, yeah. And it's not clear what these errors are, but it's also very interesting to look at them because typically they are very different from scaled white noise. But we can produce a bunch of these realization of the modeling of the dictionary compression error, and we compute the sample mean, we compute the sample covariance. So here I'm indicating that I'm using the sample, and you usually regularize it to make sure that it remains, it's a proper covariance for a Gaussian, because in the next step, we're going to say that we can think of approximating this distribution with a Gaussian centered at the sample mean and with covariance, this regularized sample covariance. Now, once we have this distribution in hand, what we can do is we can actually go ahead and we can think of the reduced, of the, let's say, yes, the compressed dictionary matching problem as a regular, let's say, linear problem, and we can whiten it. So if we take the symmetric factor of the precision matrix for the dictionary compression error, and multiply both sides from the left by subtract the mean from B and multiply by it from the left, then what we get is we get a problem in which the dictionary has been modified. So we're modifying the rows here by multiplication by this factor of the precision. And what's important is that the noise has been whitened. So we can apply everything that we know, all of the simplifications that work with white noise, and there are quite a few when one uses this Bayesian sparsity promoting algorithms to this pre-processed problem. So we compress, we compute the model discrepancy, which we call dictionary compression error, and then we whiten the reduced dictionary problem. Now we still have to, so we're continuing right now. This is an intermediate step. We don't expect to have a very good resolution of B if we're using these just the feature vectors. So we're eventually going to go back to the original, to the atoms of the original dictionary, but we want to deflate the original dictionary. So we want to drop all of the sub-dictionaries that do not play a role. So we want to identify sub-dictionaries that are contributing to B, to the representation of B. So one way of, one thing that we want to express is that of these sub-dictionaries, we only expect very few to play a role. So the algorithm that, or the problem that we want to solve can be formulated as looking for the vector H here that minimizes, and what we're minimizing here is we're minimizing the sum of the square norm of the discrepancy between of the whitened problem, between B and WH, and a term here, and I'm putting a penalty, but we will sort of get around to that. And the other thing that we want to, minimize, taking into consideration, is that we want the support of the vector that consists of, and now these are norms, but these are not two norms, these are special norms of the segments of H that correspond to the block of columns of the reduced dictionary coming from the sub-dictionaries. So we want these norms here to be of minimal support. So with this 0 here is, we are counting essentially the number of entries of this vector, which are different from 0. Now, now we need to go to the next step, or to pay, let's say, to declare what these strange norms are. And these are constructed using actually information from the full dictionary. So, before actually talking about defining these norms, I want to give a little bit of intuition as how we're going about this, because that's how we came up with this idea here. So we need to express, trademark of the Bayesian approach here, we need to express what we believe a priori to be the characteristics of the vectors that we're looking for. So in general, what we are saying, what we're thinking, we can think about Hj, so the jth the segment of H, is that it should have a structure that is similar to the columns of the column vectors of the matrix Hj, which was determined when we computed the low rank approximation of the subdictionary DJ. So it should point in that, let's say, in that general direction there. Now, in general, we could take the mean and compute it, but we don't expect it that, for a particular B, for any B that we come up with, this vector is close to the group mean, because, most of the group will not really contribute to explaining, again, even if we identify the subdictionary, there will be only few entries playing a role in the explanation of B. So in the end, what we want to say about Hj is that it should be in the general direction of Hj intended in terms of, the direction determined by its columns, but the amplitude of this vector, so how strong it should be controlled by a prior that promotes group sparsity, meaning that we want a prior that says that only a few of the subdictionaries should be active in the representation of B. So we have pretty much two levels of, or two, let's say, two statements that we can make a priori about this H. One is individual to the subdictionary from which to which it refers, and the other one is in aggregate for the subdictionary, for the role of the subdictionary. So this is how we construct, and I'm not going to go through the details of this, just to give you a sense of how this came about. So it pretty much, we are doing an SVD analysis of the matrices Hj, and we are constructing these matrices here that we're using essentially as covariance matrices for a Gaussian measure whose pullback is going to give us the what we can say about the Hj from the columns of the vectors u in the singular value decomposition of H and the ratios of the singular values, giving preference to giving stronger weight to the first one because it identifies essentially the spatial directions of the aggregate vectors of column vectors of H. So again, we can also express this in terms of conditionally distribution given the length of the vector. And if we want to express in words what these formulas here are saying, these are the formulas that we are using to compute the vector, let's say the second vector that enters in the minimization. This expresses the belief that the Hj that we're looking for, so that segment of the vector H could have a component which is arbitrarily large along the principal direction determined by the columns of H, which is along the vector u1, but it should also remain angularly and with probabilistically within the cone, which is defined by the columns of Hj. So we're giving a directional prior here. And this is what we came back with. So this is then going to be scaled by the magnitude, which is determined by the group prior. For some of the H's, for most of them, this will be very miniature, very small, but for some of them, it will be more determined. That's for the dictionaries that play a role. So we compute this H globally, and I'm going to address that in a second, in a couple of minutes. Let's say that after we have computed the vector H, then we can look at the groups, the subgroup, so it's partitioned into segments, HJs. And even though we express our preference for group sparsity, we express that most of the groups should be nearly very small. In general, we cannot expect that the norms, these new norms of the segments, will be 0 for many of them, or in fact, even for any of them. But we may expect that many of these segments of the vector H will be negligible. So what we do is we need to have a criterion to do the deflation of the dictionary. And what we go through is, since we have computed the dictionary compression error here, and in fact, we can compute the dictionary subcompression error for each one of the subdictionaries, we only say that H is significant if the contribution to B from the corresponding feature vectors is above, let's say, the noise in the representation. So we're taking the trace of this covariance here. After we've done this scoring, this thresholding here, we will have just a few, a vector with the indices to just a few of the subdictionaries that play a role, relevant role. So now that once we have identified the relevant classes, we go back to the original dictionary and we form a new reduced deflated dictionary that only contains the subdictionaries which are relevant. And now we're ready to solve the problem, the matching problem for B. And by solving this deflated problem, which in general will be quite a lot smaller, and therefore less computationally demanding than the original one. So the way in which we are solving these squares problems with sparsity promotion is the way in which we're advocating is to do it in, say, in a Bayesian sort of way. We're saying that the vector that we're looking for, in this case here I'm representing it as a vector X, because this is fairly general. And we are saying that the entries of X, we expect them to be, most of them to be 0 or very small. So we model them as independent Gaussian random variables with 0 mean and with variances that are unknown. And then if the variances are unknown in the Bayesian frameworks, they're also going to be random variables. So we need to describe those random variables, the variances, in terms of probability densities. And we think that since the variance is what is going to keep the value of X either close to the mean or allow it to, say, make it more natural to deviate from the mean, we're going to describe them in terms of independent, because we want independent entries to be large, while the neighbors are very close to 0, as independent random variables, each following, and here we can a generalized gamma distribution. This is purely for reasons of computational convenience and the positivity required for the variances here. So the thetas are representing the variances here for the x's. So and what we want to do is we call the solution the solution of a minimization problem of this type, and we can solve it by alternating these two steps until convergence is reached. So first we solve what is effectively a linear least squares problem with a matrix D, which varies from iteration to iteration. And then in the next step, once we have computed X, we update the entries of the diagonal entries of D, which are really kind of the thetas here, coming from the status, by expressing a first order optimality condition for the quantity to be minimized. So it's, this is, we've described it, it's probably 20 years we've been using this, and we call it this iterative alternating sequential algorithm when we're using the gamma distribution to describe the variances. It turns out that the function that is being minimized is convex. We can prove it that it's convex, and that this algorithm, this EIS iterates, converge to a unique minimizer. And we also have an interpretation of the minimizer in terms of the parameters of the gamma distribution. So if we take one of the parameters and we push it to -3/2, a lot of technicalities here, turns out that the solution that we compute will converge without changing norms. So while solving problems just in the two norms and an optimality condition, to what is effectively a scaled, regularized L1 solution of this type. So by applying this algorithm, F is in the limit as we make beta closer and closer to 3/2, as if we were using an L1 norm scaled by a certain quantity here. And this interpretation here is very convenient because it gives us a way of setting the parameter beta as, or thinking of the parameter beta as a knob that expresses how sparse we expect the solution to be. So very close to 3/2, very sparse, little further, more relaxed, not so sparse, not necessarily so sparse, but it's a very fast algorithm, and it can be implemented also for very large problems. If one solves the least squares problems with, for example, conjugate gradient for least squares. Now, we want to, if we solve the dictionary problem with the original dictionary, we can express the sparsity in this way. If we, when we are solving the compressed dictionary matching problem, after we've replaced the dictionary with the feature vectors, then the way in which, then again, we want to use the same algorithm, but what changes is the way in which we express our sparsity. So now we don't want to say that we expect the solution to be, let's say, generically, the solution vector H to be generically sparse, but we want to express the fact that we expect blocks, these blocks of H to be sparse or small. And so we do this by introducing, okay, a prior, which is a mix of the structural prior that I was describing before. So this is how we are measuring the the adherence to the direction of the matrix H for the block Hj, and then we have the coefficient at the scaling at the denominator here, which is a variance for the block. So one variance for the entire block here, and this is the one that we can that will over the iteration decide which one of the blocks contribute and do not contribute. So this can be all organized so that the calculations, they become fast linear algebra operations, possibly in blocks. So when we're doing EIS with both structural prior and group sparsity, then to promote the group sparsity, most of the theta j's, so most of the variances should be close to zero, because we will express it by saying that we expect the mean to be close to zero. We will have a few large outliers. Those are the contributing blocks. And then when we are combining the likelihood and this prior structural and group sparsity rich prior, what we're going to do is we're going to also consider the whitening of the problem, which is in this part here. So everything that we've learned about the dictionary and the subdictionary is going to be used here. And there is a version of the EIS that has been modified to promote sparsity and works quite well. So now let me show, because my time is, I have 10 minutes left, I want to show some computed examples. The first computed example is using a very tested data set, one that we feel that we understand more. So our original dictionary, should be D, is 300, and so we selected 834 images of handwritten digits from the NIST database. These are represented as 16 by 16 images. They are 0, 1, 3, and 9. And we throw them in, and we are agnostic about the labeling, the original labeling, because after all, it's not important for this test. We're just using this so that we have a visualization of what's going on. And we let a k-medoid algorithm cluster the dictionary. It finds that 4 classes is good, and we are plotting the coordinates projected in the LDA axis here. So we see that they're fairly well separated here. Then we run a test in which we are in sample. So we construct, at least we start in sample, we construct a B as a convex combination of a variable number of in between 1 and 3 atoms, with at most one of them from each cluster. And we don't know a priori how many of them we have. We do the reduction of the subdictionaries. So the original dictionary was 834. I had 834 atoms. Now we're going to reduce it to 3 atoms per subdictionary, so 3 feature vector per subdictionary. So we have a compressed dictionary with only 12 atoms. And now these are the feature vectors. We can visualize them in this case. And we also see that the annotation, human annotation, and the machine grouping do not always agree. And then we start seeing how this algorithm works. So we built 4,000 test problems. And now we need to evaluate what is a good performance or not. So in terms of the threshold, in terms of the support of the vector, we thresholded, saying that we consider active only the pixels which are above a certain, let's say, value to avoid numerical error. And this is small, 10 to the minus 6 and minus 7. And the way in which we decide if we've done a good job at the reconstruction is by using what is called the dissimilarity index, and which is the cardinality of the symmetric difference of the support. And now we have of the original. So this is how we built our test data is controlled experiment, and this is the retrieval. And the retrieval is at the end of phase 4. So we're going through all of the 4 phases, and we're using the deflated dictionary, where we're taking the relevant classes in full. And when these supports agree perfectly, then this similarity index is equal to 0, and the algorithm has correctly identified the atoms that constitute the data. And so we ran 4,000 tests, and 95, almost 96% of the time it does. Then what we have here is how many mistakes there are, either digits or atoms that were not there were identified, or atoms that were there were missed. So we see that the performance is quite good. And what was interesting, we tried to do some analysis on when things go bad, and we saw that even if sometimes some incorrect atoms are identified, in general, the effect of this misidentification in the relative approximation error of the data, which we are defining as the normal difference between, let's say, the datum B and the approximation divided by the normal B, may be fairly small. So, and what is nice is that one can actually monitor serious failures of the algorithm, because when it really fails, then this indicator here is, becomes large. And this can be computed without knowing. So one can look at the performance using this as a proxy for the error without knowing X. And so this was quite nice. And we tested with respect to tau. And we saw that let's say, this is how many, this is the relative error that we compute, but we don't know how to evaluate in general. And this is corresponding to the cases where, let's say, this proxy was less than 0.05. So it's a very good performance here, or 0.1. So we have identified a fault detection mechanism. And in this case, the dictionary compression error was not very significant, but it plays an important role, like a perfect recall or versus total failure in another computed example that we did with glitches classification from the LIGO Virgo experiment here. So we took it, and I think I'm done. I think I'm out of time, right? Yeah. So what we have here is what we have worked at, and we're in the process, and I'm gonna sort of finish here. This is being written up, and it will be put on archive. And by the end of the weekend here, is that using this, we can use this Bayesian framework pretty much all the way through this dictionary calculations, dictionary tasks, to model the error when we're compressing the dictionary, to use to build sparsity promoting priors that are conforming to, let's say, partitioning of dictionaries, and also we can tune the sparsity to correspond to what we believe a priori, and in the process of doing so, we have discovered that we can monitor the mistakes that are made in this dictionary matching without knowing the exact solution by finding, say, computable proxies that are not computationally heavy, but they give a good indication, at least give good warnings that when they are large, these quantities, then the matching should not be trusted. And right now we're applying this to signals from MRI and tomography. Thank you.